All right, welcome to day one of differential equations. This is section 1.1, 1.2, and 1.3, three sections. So we should probably, since this is a class on differential equations, we should probably define what a differential equation is. So let's start with a definition. Again, this is sections 1.1, 1.2, and 1.3. Again, we need to define a differential equation. We've seen differential equations before. We've interacted with them. We perhaps even have defined them previously, but to be clear, an equation containing the derivative of one or more dependent variables, the derivatives of one or more dependent variables with respect to one or more independent variables is a differential equation. We usually will just abbreviate differential equation as DE, or sometimes diff EQ. That is to say, a differential equation is an equation involving a derivative. We don't care how many derivatives, we don't care what the derivative of. Just if it's an equation that has a derivative, it is a differential equation. Coupled with this, we have a solution free of arbitrary parameters is called a particular solution. We often will say that obviously something is true if it makes a statement true. A statement is a solution if it makes something true. For instance, if I have the equation 2x minus y equals 4, well, this has solutions 0, -4. It has the solution 2, 0. It has the solution 1, -2, and I could literally keep going forever here. There are an infinite number of solutions to this, but a solution is something which makes it a true statement. So a solution to a differential equation is going to be an equation which, when plugged into the differential equation, gives us a true statement. Now, when talking about differential equations, we classify them using a number of different criteria, but to start with, we're going to say we classify differential equations based on 3 categories. First, we classify them by type. Second, we classify them by order. And third, we classify them by linearity. Now, when I say type, the two types of differential equations are considered to be ordinary differential equations and partial differential equations. When I talk about order, in the same way, like when we talk about an algebraic equation, we classify it based on, like, if I'm talking about a polynomial, well, this is to the first power, the second power, third power, and so on. We have the same idea with differential equations, but since differential equations are concerned about derivatives, we talk about, in classifying order, we talk about what is the highest power of derivative that's taken. So order is specifically the order of the highest derivative present in the problem. And then linearity, something is either linear or it's not linear. We're going to modify our definition or our understanding of linear a little bit from previous classes. But when I say linearity, I mean this is linear in a dependent variable. And I know all of these need a little bit more clarification, except perhaps for order. So let's now look at some clarification. So, for example, if I give you the differential equation dy dx plus 5y is equal to e to the x. Now, this is a differential equation. It is a differential equation because it is an equation which involves a derivative. Differential equation. Now, the next question is it, since we understand that it's a differential equation, what is its type, what is its order, and what is its linearity? Now, this is of type ordinary. And I'll get into why in a minute, but its type is ordinary. Its order is that it is a first order. This is Kylo Ren's favorite. And then with regard to its linearity, this is linear in y. So we say that this is linear. Y being the dependent variable, it is linear in y. So in this example, this is an ordinary first order linear differential equation. So let's change one aspect about this. If I make this the second derivative of y with respect to x plus 5y is equal to e to the x, this is still a differential equation because it's still an equation involving a derivative. In classifying this, it's still ordinary and it is still linear. What I've changed about this is the derivative taken. It's not the first derivative, but we've got a second derivative. So this is second order. And we could imagine, I mean, we could have an equation where we've got the 16th order derivative, right? Or the 16th derivative. So that would be a 16th order differential equation. So let's contrast this with a nonlinear differential equation. So if I modify this further, say d squared y dx squared plus 5y times y prime is equal to e to the x. It's still ordinary. It is still second order because the second derivative is still present. But now this is nonlinear. It's nonlinear in the dependent variable. The dependent variable here is y, and it's nonlinear in y because we have a y times a y prime. Anytime I have in the equation a y times a y, or a y times y prime, or y prime times y triple prime, any of that stuff, anytime I've got the dependent variable times itself, or the dependent variable times a derivative of itself, or any derivative of the dependent variable times the derivative of a dependent variable, it is no longer linear. So that is the demarcation between linear and nonlinear. One I haven't played around with though, like all of our examples have been ordinary. We can now identify the order. We can now identify hopefully whether it's linear or nonlinear, but we haven't talked about what it means to be ordinary versus, and then the other one is partial. So I'm going to give you another example. This one is going to fail to be ordinary. And its family will never let it forget it. So one that fails to be ordinary is if I tell you I've got some function, and then we might say that the derivative of that function, the second derivative of that function with respect to x minus the second derivative of that function with respect to y is equal to 2x. Now, this is still linear, because at no point do I have any derivatives of f multiplied by each other, or do I have f multiplied by any of its derivatives, or f times f. So it's still linear. I have second derivative present. I have second derivative with respect to x and second derivative with respect to y. So this is the second order. But there are two independent variables here. We have x and y as independent variables. So this is partial. So when we're classifying something as partial or ordinary, we're looking to see how many independent variables are there. If there's only one independent variable, it is an ordinary differential equation. If there are two independent variables, then it is, or more, then it is a partial differential equation. We look at the highest order of the derivative, that is the order of the differential equation, and we look to see if any of our dependent variables are multiplied by each other or their derivatives. And that's how we classify differential equations at this stage. So now we're going to have some examples. So let's look at, say, dy dx minus 3y equals 0. Let's look at y double dot squared minus y dot is equal to negative 6x. Let's look at x prime squared plus y prime squared equals 5. And let's look at d squared u dy squared plus dy dx is equal to 0. So we're going to pause this for a minute. Go ahead and classify these using type, order, and linearity. Go ahead and classify these differential equations. And then when you've done that, go to the next video.